Welcome to Sleepy Science Facts, where the mysteries of the universe unfold in the calmest way possible. Tonight, we're drifting into the glowing spiral of our cosmic home, the Milky Way. In the next few hours, you'll discover how our galaxy was born, what secrets lie at its center, and why it's far more mysterious than it looks in the night sky. So settle in, relax, and let your curiosity drift among the stars. And before we begin, make sure to like, subscribe, and hit the bell icon for more sleepy science facts. And of course, read the first command for support. All right, let's float into the Milky Way. Above us, stretching across the night sky, lies a river of light, a luminous band of stars, dust, and gas, woven together over billions of years. This is the Milky Way. To our eyes, it appears as a gentle smear across the heavens, yet within its vast expanse lies a story older than time itself. Every glimmering point of light, every shadow between, is a chapter in the cosmic saga of creation and destruction, of matter and energy, of life and death. And we are part of this story. A small planet circling a modest star, tucked within one of its swirling arms, quietly carrying life in a universe both terrifying and beautiful. Tonight, we embark on a journey, not merely to observe, but to understand, to feel, and to witness the intricate dance of our galaxy, the Milky Way, in all its glory and mystery. Birth of the Milky Way billions of years ago, long before the Earth had even formed, the universe was a very different place. Following the Big Bang, the cosmos was a vast sea of hydrogen and helium, punctuated by the first faint glimmers of matter beginning to coalesce under gravity's unyielding pull. These primordial clouds drifted through the void, colliding, merging, and spinning into the earliest seeds of galaxies. Among them, one would become our home, the Milky Way. The birth of the Milky Way was not a singular event, but a symphony of countless cosmic processes. Gravity drew together clouds of gas, igniting nuclear fusion at their cores. The first stars, massive, brilliant, and short-lived, blazed into existence, their ultraviolet light shaping the surrounding gas, triggering waves of star formation. As these early stars lived and died in spectacular supernovae, they scattered heavier elements, carbon, oxygen, iron, throughout the galaxy, seeding the material for future generations of stars, planets, and eventually life itself. Modern astronomers, using instruments like the Hubble Space Telescope and the Gaia Observatory, have painstakingly mapped the motions of millions of stars, revealing a galaxy not static, but in constant motion, a spiraling, rotating structure shaped by collisions with smaller galaxies over eons. Each star in our night sky carries a piece of this ancient history, a cosmic fingerprint tracing back to the turbulent youth of the Milky Way. To imagine the scale is to confront the sublime. The Milky Way is home to more than 100 billion stars, with at least 100 billion planets orbiting them. Its spiral arms stretch tens of thousands of light years, curving gracefully around a central bulge of older stars. Yet, despite this immensity, we have only begun to understand its complexity. Each arm, each cluster, each interstellar cloud is a living record of the galaxy's evolutionary history, whispering secrets of creation and destruction across time and space. Consider the Sun, our modest, yellow star, formed roughly 4.6 billion years ago in one of the Milky Way's spiral arms. Its birth was not a quiet event, but the result of shock waves from earlier supernovae compressing gas clouds, igniting fusion at last. Around it, planets coalesced from the remaining dust and gas, spinning into orbits governed by the subtle balance of gravity. And on one small, rocky world, conditions aligned in such a way that life began, a biological echo of the galaxy's restless, creative energy. The Milky Way is more than stars and planets. It is a living archive, a dynamic ecosystem of celestial phenomena. Between its stars lie vast clouds of molecular gas, the nurseries of future suns. Invisible to our eyes, dark matter threads through its structure, holding it together, influencing its rotation and dictating its ultimate fate. Magnetic fields ripple across its spiral arms, guiding the flow of charged particles, shaping star formation in ways only now becoming clear. At its very heart lies a supermassive black hole, Sagittarius A gravitational anchor around which millions of stars whirl in silent, eternal motion. The story of the Milky Way is a story of time itself. Billions of years of collisions, births, and deaths of stars have sculpted its shape, each event leaving traces detectable by modern science. Spectroscopy allows us to read the chemical composition of stars, revealing their ancestry. Stellar motion studies tell us about past galactic mergers. Infrared surveys pierce through dust clouds, uncovering hidden regions of star formation. And yet, for all our instruments and measurements, the galaxy remains a place of wonder, a realm that challenges our imagination and humbles our perspective. In this chapter, we have begun to glimpse the Milky Way's origins, the violent yet creative forces that gave it shape. We have touched the echoes of its first stars, witnessed the seeding of the elements that would one day make planets and life possible. But the Milky Way is more than its beginnings. Its story is ongoing, written in the orbits of stars, the formation of nebulae, and the collisions of clouds of gas. In the chapters to come, we will journey deeper into its spiral arms, into its stellar nurseries, and into the mysteries that still lie hidden in the dark spaces between the stars. Spiral arms, star formation, and nebulae. As we move outward from the galactic center, the Milky Way reveals a structure both delicate and immense, a spiral of luminous arms, each winding gracefully around the core like ribbons of light stretching across the cosmos. These spiral arms are not merely decorative, they are engines of creation, where stars are born, live, and die, fueling the perpetual cycle of cosmic evolution. Observations show that the Milky Way has 4 primary spiral arms, each densely packed with young, hot stars, clouds of gas, and interstellar dust. Within these arms, immense molecular clouds, some spanning hundreds of light years, collapse under their own gravity, giving birth to new stars. These regions, called stellar nurseries, are the cradles of future suns. The Orion Nebula, visible even with modest telescopes, is one such nursery, where hundreds of young stars ignite, their intense radiation sculpting the surrounding gas into intricate shapes, resembling celestial sculptures. Star formation is a delicate balance. Gravity must overcome the outward pressure of the gas within the cloud. Shockwaves from nearby supernovae or colliding clouds can trigger the collapse, compressing the gas into dense cores that eventually ignite nuclear fusion. When fusion begins, the star shines for millions to billions of years, radiating energy across the galaxy. Yet, this is only the beginning of a star's story. The stars we see today are the descendants of countless generations, each contributing new elements to the galactic environment. Consider the Pleiades cluster, a dazzling grouping of young stars often called the Seven Sisters. Each star here is only tens of millions of years old, a cosmic infant compared to our sun's 4.6 billion years. These stars illuminate the surrounding dust, creating reflection nebulae that scatter blue light into the night sky. Such clusters are ephemeral. Gravitational forces gradually disperse the stars over millions of years, blending them back into the galactic population. Yet, even in their temporary brilliance, they shape the Milky Way, seeding nearby regions with stellar winds and radiation that influence the next wave of star formation. But not all regions of the galaxy are equally productive. Some arms are dense, bustling with young stars and glowing gas clouds, while others are more quiescent, populated by older, cooler stars. Between these arms lie vast stretches of dark matter and interstellar medium, mostly invisible yet critically important. The unseen mass of dark matter stabilizes the galaxy's rotation, preventing the stars at the outer edges from flinging into intergalactic space. Without it, the Milky Way as we know it could not exist. Nebulae, the clouds of gas and dust within the spiral arms, tell the story of both life and death. Some, like the Orion and Eagle nebulae, are regions of active star formation. Others, like the Crab Nebula, are remnants of stars that have ended their lives in supernova explosions. When massive stars explode, they scatter heavier elements into space, enriching the surrounding clouds with carbon, nitrogen, oxygen, and iron, the very building blocks of planets and life. In this way, death fuels creation, and the Milky Way continues to grow and evolve. Astronomers have mapped these spiral arms using radio telescopes, infrared observations, and the motion of stars. They reveal a galaxy alive with motion, spiral density waves propagating through the disk, triggering bursts of star formation as they pass. This dynamic environment is responsible for the majestic patterns we observe from Earth, as well as the ongoing creation of stars that may one day host planets, perhaps even life. The study of star formation is more than just observing light. It is a window into the fundamental processes that shape galaxies. By analyzing the chemical composition of nebulae, we learn about the elements available for planet formation. By studying the motion of gas and dust, we understand the forces driving galactic evolution. And by observing young stars and clusters, we glimpse our own sun's history, remembering that it too was once a newborn in a swirling cloud of gas and dust. In this chapter, we have explored the spiral arms of the Milky Way, the stellar nurseries that light up the galaxy, and the intricate nebulae that bear witness to the cycle of life and death in space. These structures are more than beautiful. They are the active heartbeat of our galaxy, shaping not only the stars we see, but also the future of the Milky Way itself. As we continue our journey, we will venture further into the lives of stars, witnessing their transformations, their violent ends, and the extraordinary phenomena that mark their passage through the cosmos. The life and death of stars. Stars are the engines of the Milky Way, the fundamental building blocks that illuminate and shape our galaxy. Yet, like all things in the universe, they are born, they live, and ultimately they die. The story of a star is a story of balance, a delicate struggle between the inward pull of gravity and the outward pressure generated by nuclear fusion in its core. For millions or even billions of years, this balance sustains a star, allowing it to shine steadily, radiating energy across the galaxy. But eventually, all stars reach the limits of their fuel, and their lives take dramatic turns that can reshape the cosmos around them. The journey begins in a cold, dark molecular cloud, where gravity slowly pulls gas and dust together. Within these clouds, pockets of matter condense, forming protostars. Initially dim and shrouded in dense material, these protostars gradually ignite fusion in their cores. Hydrogen begins to fuse into helium, and a new star is born. Its light pierces the surrounding dust, marking the beginning of its long journey as a stellar beacon. The path a star follows depends on its mass. Low-mass stars, like our Sun, live for billions of years, burning their hydrogen steadily. They shine with a gentle light, relatively stable, providing warmth and energy to any surrounding planets. When they exhaust their hydrogen, they expand into red giants, shedding outer layers in a glowing display that seeds the surrounding space with enriched gas. Finally, they collapse into white dwarfs, slowly cooling remnants of what was once a brilliant sun. High-mass stars, by contrast, lead shorter but far more dramatic lives. Burning through their fuel at astonishing rates, they can exhaust their hydrogen in mere millions of years. Once their cores can no longer support fusion, gravity wins. These stars collapse violently, resulting in supernova explosions of unimaginable power. In a fraction of a second, a star can outshine its entire galaxy, scattering elements forged in its core across space. Carbon, oxygen, silicon, iron. These are the building blocks of planets, of life, cast across the Milky Way for future generations of stars to inherit. Some of these supernovae leave behind extraordinary remnants. Neutron stars, composed almost entirely of densely packed neutrons, rotate at incredible speeds, emitting beams of radiation visible across light years. Others collapse further, forming black holes, regions where gravity is so intense that not even light can escape. Sagittarius A, the supermassive black hole at the center of our galaxy, is the ultimate example, anchoring the Milky Way and influencing the motion of millions of stars around it. The death of a star is not the end of the story, it is transformation. The elements produced in stellar cores and distributed through explosions enrich the interstellar medium, ensuring that every new star and planet is made from the remnants of previous generations. In this way, the galaxy recycles its material, creating a continuous cycle of birth, death, and rebirth. Take Betelgeuse, the red supergiant in Orion, for instance. This colossal star is nearing the end of its life. Once it explodes in a supernova, its light will briefly rival the moon in brightness, a spectacular reminder that stars are alive, dynamic entities. Nearby, the Crab Nebula, the remnant of a supernova observed in 1054 AD, continues to expand, a cosmic monument to stellar death that still emits energy detectable across the galaxy. Stars also shape the Milky Way in subtle ways. Their radiation influences the formation of neighboring stars, carving intricate structures in nebulae. Stellar winds, streams of charged particles expelled from stars, push and compress interstellar gas, triggering waves of star formation in some regions while suppressing it in others. Every star, every death, every explosion is a note in the ongoing symphony of the galaxy. Observing these processes is no simple task. Modern astronomers use an array of tools to study the life cycle of stars. Telescopes spanning the electromagnetic spectrum, from radio waves to gamma rays, reveal hidden nurseries, violent supernovae, and the faint glow of distant white dwarfs. Spectroscopy allows scientists to determine the chemical composition of stars, uncovering clues about their origin and evolution. And Gaia, the European Space Agency's ambitious star mapping mission, has charted the motions of more than 1 billion stars, revealing the dynamics of our galaxy in unprecedented detail. Understanding stars is crucial because they are the architects of the cosmos. Without their fusion, there would be no light, no heat, no elements heavier than hydrogen and helium. Without their death, there would be no planets, no complex chemistry, no life. Every atom in our bodies was forged in a star, and every star in the Milky Way carries the history of the cosmos within it. In this chapter, we have journeyed through the birth, life, and death of stars. We have witnessed the gentle glow of sun-like stars, the violent demise of massive supergiants, and the astonishing remnants left behind, neutron stars and black holes. This cycle of creation and destruction is the heartbeat of the Milky Way, a rhythm that has persisted for billions of years and will continue for billions more. And yet, the galaxy holds even more mysteries, waiting in the vast darkness between its stars. The galactic center and the heart of the Milky Way, at the very center of our galaxy lies a region of mystery, power, and unimaginable density. The galactic core, hidden behind thick clouds of gas and dust, is home to Sagittarius A, a supermassive black hole with a mass of more than 4 million suns. Around it, stars orbit at incredible speeds, tracing paths dictated by the invisible grip of gravity. Observing this region is like peering into the heart of the Milky Way itself, revealing both the violence and elegance of the cosmos. The environment near the galactic center is extreme. Stellar densities reach levels thousands of times greater than in our solar neighborhood. Stars crowd together, interacting gravitationally, sometimes exchanging orbits or even colliding. Gas clouds, heated to millions of degrees by intense radiation, swirl around in complex patterns. Yet amidst this chaos, order emerges. Stars orbit Sagittarius A with predictable paths, and the dynamics of this region help astronomers measure the mass and properties of the black hole with astonishing precision. For decades, scientists could only infer the existence of Sagittarius A indirectly, observing the motion of stars near the center and the radiation emitted from gas clouds being consumed by its immense gravity. Then, in 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, confirming what theories had predicted for decades. This was not just a technical achievement. It was a glimpse into the invisible heart of our galaxy, the anchor around which the Milky Way rotates and evolves. Surrounding the black hole are dense clusters of stars, some newly formed, others ancient relics from the earliest epochs of the galaxy. These clusters, like the arches and quintuplet clusters, are laboratories for understanding stellar evolution under extreme conditions. The intense gravitational environment accelerates stellar processes, influencing the formation of massive stars, the evolution of binaries, and even the eventual fate of supernova remnants. Here, life and death of stars occur at a pace unlike any other region in the galaxy. But the galactic center is not solely dominated by stars. Dark matter, invisible yet pervasive, exerts its influence even here, contributing to the rotation curve of the Milky Way and stabilizing the overall structure. Magnetic fields twist and tangle, guiding charged particles, shaping jets and outflows, and playing a crucial role in the transfer of energy within the core. This is a region where the visible and invisible coexist, where ordinary matter and dark matter interact in ways we are only beginning to understand. Observations across multiple wavelengths, from X-rays to radio waves, have revealed extraordinary phenomena. Massive clouds of gas collide, creating shock waves that trigger bursts of star formation. Stellar winds from young, hot stars carve cavities in surrounding material. Occasionally, stars venture too close to the black hole, stretching into elongated shapes in a process called tidal disruption. These events, rare yet spectacular, remind us that the galaxy is alive, dynamic, and dangerous. The galactic center also provides insight into the history of the Milky Way. By studying the composition of stars near Sagittarius A, astronomers can trace the chemical enrichment of the galaxy, the sequence of star formation, and the evidence of past mergers with smaller galaxies. Every star in the core is a fossil, preserving clues about the forces that shaped the Milky Way billions of years ago. And yet, despite the violence and density, there is beauty. The dance of stars around the black hole is a cosmic choreography, an elegant interplay of gravity, motion, and time. Even the dark matter, though invisible, contributes to the grand design, keeping the galaxy's spiral arms coherent and allowing life in the outer regions, like our sun's home, to flourish in relative stability. The galactic center is a microcosm of the Milky Way's complexity, a place of extremes where gravity and energy converge, where creation and destruction coexist, and where the forces that shape our galaxy are on full display. Understanding this region is not merely an academic pursuit. It is a journey into the very mechanisms that govern the universe, offering a glimpse into the processes that have influenced every star, every planet, and every atom in our galaxy. As we move outward from the core, we carry with us the knowledge of this intense environment. The Milky Way is more than the sum of its stars. It is a dynamic system, bound by gravity, enriched by stellar evolution, and energized by the interplay of matter and dark matter. In the chapters to come, we will explore the vast disk of the galaxy, the halo of ancient stars, and the enigmatic dark matter that silently holds it all together, shaping the Milky Way in ways both subtle and profound. The galactic disk, halo, and globular clusters. Beyond the chaotic heart of the Milky Way lies a region of subtle, elegant structure, the galactic disk. This flattened plane stretches tens of thousands of light years across, a swirling stage upon which the drama of stars, gas, and dust unfolds. Here, the majority of the galaxy's stars reside, including our sun, orbiting the center in nearly circular paths, tracing a silent ballet dictated by gravity. The disk is both orderly and alive, a testament to the intricate forces shaping the Milky Way. The disk is divided into two components, the thin disk and the thick disk. The thin disk is home to young stars, open clusters, and vast clouds of gas and dust. It is the cradle of ongoing star formation, where stellar nurseries illuminate the surrounding regions with newborn light. The thick disk, in contrast, contains older stars, relics of the Milky Way's early formation, moving in slightly more elliptical orbits and enriched with heavier elements formed in generations of prior stars. Together, these layers weave the fabric of the galaxy, a living record of cosmic history written in starlight. Interspersed within the disk are striking formations of gas and dust, nebulae, supernova remnants, and molecular clouds. The Eagle Nebula, with its iconic pillars of creation, offers a window into the delicate process of star birth. Within these towering columns, gravity coaxes gas and dust into dense clumps, eventually igniting fusion to form stars. Each new star contributes to the energy, dynamics, and chemical enrichment of its surroundings, continuing the cycle that has sustained the galaxy for billions of years. Above and below the disk lies the galactic halo, a sparse, spheroidal region containing ancient stars, globular clusters, and vast amounts of dark matter. Globular clusters, dense collections of up to 1 million stars, orbit the galaxy in the halo, remnants of its earliest epochs. They are some of the oldest known objects in the universe, preserving the chemical fingerprints of a time when the Milky Way was just beginning to take shape. By studying these clusters, astronomers can trace the assembly history of our galaxy, revealing evidence of mergers with smaller galaxies that helped build the Milky Way into the spiral we see today. Dark matter, though invisible, dominates the mass of the halo. It exerts a gravitational pull that stabilizes the disk, influencing the rotation speeds of stars far from the center. Observations show that stars in the outer regions of the Milky Way rotate faster than expected if only visible matter were present. This discrepancy led scientists to hypothesize the presence of dark matter, an elusive substance that shapes galaxies across the cosmos. Though it cannot be seen directly, its influence is felt everywhere in the Milky Way, silently sculpting its form and guiding its evolution. Among the halo's ancient stars are relics of the first galaxies absorbed by the Milky Way. Streams of stars, remnants of tidal interactions, stretch across the sky like ghostly trails, evidence of collisions and mergers over billions of years. The Sagittarius stream, for instance, is composed of stars torn from a dwarf galaxy that continues to be devoured by the Milky Way. Each stream is a fragment of history, a reminder that our galaxy is not static, but the product of countless cosmic interactions. Within the halo, globular clusters shine like cosmic jewels. Omega Centauri, the largest known globular cluster in the Milky Way, contains millions of stars tightly bound by gravity. Observing these clusters reveals the chemical composition and dynamics of the early universe, offering insights into how galaxies like ours assembled over cosmic time. Their stars, often older than 10 billion years, are living fossils, preserving the memory of the first generations of stellar formation. The galactic disk and halo together form a dynamic, interconnected system. Stars migrate between regions, influenced by gravitational interactions, spiral density waves, and tidal forces. Gas expelled by dying stars in the disk eventually cools and rains back, feeding future star formation. Dark matter provides the invisible scaffolding upon which this complex structure rests. Each element, the disk, the halo, the clusters, and the unseen matter, works in harmony, sustaining the Milky Way's architecture and ensuring its continuity across billions of years. From our vantage point within the disk, we see the Milky Way as a luminous band arching across the sky. Yet this view conceals the vast complexity of its structure. Beyond the stars visible to the naked eye lies a rich ecosystem of stellar populations, dark matter, and gas clouds, each playing a crucial role in the galaxy's evolution. By mapping these components, astronomers have transformed our understanding of the Milky Way from a simple spiral of stars into a living, breathing entity, a galaxy with history, dynamics, and ongoing creation. In this chapter, we have explored the disk, the halo, and the globular clusters of the Milky Way, uncovering the patterns and forces that shape its structure. We have seen how young stars and gas clouds populate the thin disk, how the thick disk preserves the record of past generations, and how ancient clusters and streams reveal the history of galactic mergers. And we have glimpsed the invisible hand of dark matter, silently guiding the motion of stars and stabilizing the galaxy as a whole. The Milky Way, in all its complexity, is not merely a collection of stars. It is a dynamic system, alive with history, motion, and potential. The interstellar medium, gas, dust, and cosmic alchemy, between the stars of the Milky Way lies a vast, nearly invisible ocean, the interstellar medium. Composed of gas, dust, and high-energy particles, this seemingly empty space is, in fact, the lifeblood of the galaxy. It is within these clouds that new stars are born, where elements forged in the hearts of dying stars are recycled, and where the delicate processes of cosmic alchemy take place. Though the void may appear silent, it is filled with motion, energy, and the potential for creation. Hydrogen, the simplest and most abundant element in the universe, dominates the interstellar medium. It forms colossal molecular clouds that can span hundreds of light years, cold and dense, yet teeming with potential. Within these clouds, regions of higher density collapse under gravity, forming the seeds of new stars. These stellar nurseries are often cloaked in thick dust, invisible to optical telescopes, but illuminated when observed in infrared or radio wavelengths, revealing the intricate web of filaments, clumps, and cavities where stars will soon ignite. Dust, though a small fraction of the interstellar medium by mass, plays an outsized role. Tiny grains of carbon, silicon, and ice absorb and scatter starlight, shaping the appearance of nebulae and influencing the thermal balance of the gas. They act as catalysts for chemical reactions, allowing simple molecules to combine into more complex compounds. In some regions, dust grains provide the surfaces upon which molecules like water, methane, and even organic compounds form, laying the groundwork for the chemistry necessary for life. Cosmic rays, high-energy particles traveling near the speed of light, thread through the interstellar medium, influencing the ionization and chemistry of gas clouds. Though invisible, they play a subtle but critical role in regulating star formation, shaping magnetic fields, and distributing energy throughout the galaxy. Every component of this medium, the gas, dust, and cosmic rays, interacts in a complex dance, maintaining the Milky Way as a dynamic, evolving ecosystem. The interstellar medium is not static. Shock waves from supernovae plow through surrounding gas, compressing it, heating it, and triggering new bursts of star formation. Stellar winds from massive stars carve cavities and tunnels in nearby clouds, shaping the structure of nebulae. The Eagle Nebula, pillars of creation, are perhaps the most famous example, towering columns of gas sculpted by the radiation from young, massive stars. Within these pillars, new stars are being born even now, a vivid testament to the ongoing cycle of life and death in the galaxy. Some of the largest star-forming regions in the Milky Way, like the Orion Molecular Cloud Complex and the Carina Nebula, are laboratories of cosmic activity. In Orion, we see stars in every stage of development, from protostars cocooned in dense dust, to young stars igniting fusion, to clusters of massive O-type stars illuminating their surroundings. Carina, larger and even more energetic, hosts some of the most massive stars known, including Eta Carini, a star so luminous and unstable that its eruptions could be seen across the galaxy. These regions are not only beautiful, they are evidence of the forces that continually shape the Milky Way. Supernovae play a pivotal role in enriching the interstellar medium with heavy elements. When massive stars end their lives in colossal explosions, they disperse carbon, oxygen, iron, and other elements forged in their cores into surrounding gas. These elements mix with existing material, contributing to the chemical diversity of future stars and planets. In this way, each generation of stars builds upon the last, passing on the ingredients necessary for complexity and, ultimately, life. The interstellar medium also connects the small with the large, the individual stars with the entire galaxy. Spiral density waves propagate through the disk, compressing gas in the arms and triggering star formation in a rhythmic pattern. Magnetic fields thread through clouds, guiding charged particles and influencing the collapse of gas into stars. Cosmic processes occurring on scales of light years shape structures visible across thousands of light years, reminding us that the Milky Way is an interconnected system, where every part affects the whole. By studying the interstellar medium, astronomers uncover the mechanics of galactic evolution. Spectroscopy reveals chemical abundances, radio observations map the distribution of gas, and infrared imaging unveils hidden nurseries. Together, these tools allow scientists to understand not only where stars form, but how the galaxy as a whole grows and evolves. The Milky Way, once thought to be a static band of stars, is now recognized as a dynamic, living entity, with the interstellar medium serving as its circulatory system, distributing matter, energy, and the potential for life. In this chapter, we have explored the invisible yet essential fabric of the Milky Way, the interstellar medium. We have seen how gas, dust, and cosmic rays interact to give birth to stars, how supernovae enrich the galaxy with the elements of life, and how vast molecular clouds serve as the cradles of creation. This medium, often overlooked, is a reminder that the galaxy is not merely a collection of stars, but a dynamic ecosystem, alive with processes that span millions of years and countless light years, shaping the destiny of the Milky Way and everything within it. Planetary systems and the diversity of worlds, as we move from the stars themselves to the worlds that orbit them, the Milky Way reveals yet another layer of complexity and wonder. Planetary systems are not rare exceptions. They are an intrinsic part of the galaxy's architecture. Around most stars, disks of gas and dust collapse under gravity to form planets, moons, asteroids, and comets, a process both delicate and violent, driven by forces that can sculpt worlds in endless variety. These systems, though small on a galactic scale, hold the promise of life, the potential for ecosystems, and the echoes of cosmic history. Our own solar system offers a familiar blueprint: rocky planets close to the star, gas giants farther out, icy bodies at the periphery. But as astronomers have discovered, the Milky Way is home to planetary arrangements far stranger and more diverse. Some planets orbit perilously close to their stars, completing a revolution in mere hours, their surfaces scorched and molten. Others are massive gas giants, larger than Jupiter, orbiting at great distances, some in eccentric orbits that defy our solar system's orderly pattern. The galaxy is a laboratory of possibilities, a testament to the boundless creativity of cosmic formation. The search for exoplanets, planets beyond our solar system, has revealed thousands of worlds, many in environments once thought inhospitable. The Kepler Space Telescope, launched in 2009, transformed our understanding of planetary diversity. It discovered planets in tight resonance chains, Earth-sized worlds in habitable zones, and gas giants orbiting distant stars. TRAPPIST-1, a star just 40 light-years away, hosts 7 Earth-sized planets, 3 of which lie within the region where liquid water could exist. Proxima Centauri b, orbiting our nearest stellar neighbor, is a tantalizing possibility for habitability, reminding us that life may find a foothold even in alien conditions. Planet formation is intimately connected to the life cycle of stars. When stars form from molecular clouds, they retain a surrounding protoplanetary disk of gas and dust. Within these disks, dust grains collide and coalesce, forming planetesimals, the building blocks of planets. Over millions of years, these planetesimals grow, merge, and sometimes fragment, sculpted by the gravity of neighboring bodies. The resulting diversity is immense. Rocky worlds, gas giants, ice-rich moons, and exotic planets with atmospheres of methane, carbon dioxide, or hydrogen. The Milky Way is also home to rogue planets, worlds that drift alone through interstellar space, unbound to any star. These lonely travelers, hidden in the darkness, are invisible except when they pass in front of background stars, their presence inferred by subtle gravitational effects. Their existence reminds us that planetary formation is not always orderly, that chaos and chance shape the destiny of worlds as much as gravity and chemistry. Planetary systems are more than celestial curiosities. They are archives of galactic history. The composition of planets reflects the chemical abundance of their parent stars, which in turn depends on the generations of stars that came before. Worlds rich in heavy elements, iron, silicon, oxygen, are products of countless supernovae and stellar winds recycled through the interstellar medium. In this way, every planet is a living record of the Milky Way's evolution, a material link to the ancient stars that forged the elements of life. The discovery of these diverse worlds has profound implications. They expand our understanding of the conditions under which planets, and potentially life, can exist. They challenge long-held assumptions and invite us to imagine the extraordinary possibilities of alien landscapes. In a galaxy of hundreds of billions of stars, even if only a fraction host planets capable of supporting life, the number of potentially habitable worlds is staggering. The Milky Way is not just a home for stars. It is a home for worlds, each with its own story waiting to be told. In this chapter, we have journeyed through the planetary systems of the Milky Way, from familiar analogs to our own solar system, to the exotic and unexpected arrangements revealed by modern astronomy. We have explored the processes that shape planets, the diversity of environments in which they form, and the profound connections between stellar evolution and planetary chemistry. Each planet, each moon, and each rogue world is a testament to the creativity of the cosmos, reminding us that the galaxy is alive with possibility, teeming with worlds yet to be explored, and perhaps, somewhere, harboring life like our own. The Milky Way in motion, rotation, interactions, and galactic collisions. The Milky Way is not a static island in space. It is a living, moving entity, swirling through the cosmos with grace and power. Every star, every cloud of gas, every dark matter halo participates in a vast celestial dance dictated by gravity. Our galaxy rotates, completes its revolutions, and interacts with neighbors, revealing a history written not in stone, but in motion, a dynamic choreography spanning billions of years. The rotation of the Milky Way is a story in itself. Stars in the disk orbit the galactic center at incredible speeds, some traveling hundreds of kilometers per second. Yet their motion is not uniform. Stars near the core move faster, influenced by the dense mass of the central bulge and the supermassive black hole, while stars farther out in the spiral arms are governed by the subtle, invisible pull of dark matter. This discrepancy, observed in the 1970s by astronomers Vera Rubin and Kent Ford, provided some of the first compelling evidence for dark matter, a mysterious substance that exerts gravitational influence without emitting light, shaping the Milky Way and countless other galaxies across the universe. Beyond rotation, the Milky Way is constantly interacting with its neighbors. Our galaxy is not isolated. It belongs to a cluster of galaxies known as the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Gravitational forces pull these galaxies toward each other, triggering interactions that stretch, distort, and sometimes consume. Streams of stars, torn from smaller galaxies like the Sagittarius dwarf, wrap around the Milky Way, relics of collisions that occurred billions of years ago. These stellar streams are ghostly traces of a turbulent past, reminders that our galaxy has grown not in isolation, but through accumulation and merger. The future of the Milky Way is no less dramatic. Astronomers predict that in approximately 4 billion years, the Milky Way and Andromeda galaxies will collide. This cosmic event, slow and majestic on human timescales, will dramatically reshape both galaxies. Stars will be scattered into new orbits. Gas clouds will compress and trigger waves of star formation, and the central black holes may merge, unleashing enormous amounts of energy. Though individual stars, including our Sun, are unlikely to collide directly, the gravitational upheaval will transform the structure of the galaxy, creating a new, larger elliptical galaxy, a fusion of two spiral titans. Even smaller interactions are significant. Dwarf galaxies that venture too close are gradually torn apart by tidal forces, their stars absorbed into the Milky Way's halo or disk. The Sagittarius Stream, a vast arc of stars, exemplifies this process, providing a living record of the Milky Way's appetite for growth. Each merger contributes to the evolution of the galaxy, redistributing mass, altering chemical compositions, and seeding the interstellar medium with fresh material for new generations of stars and planets. These motions and interactions are not random. They are guided by the invisible scaffolding of dark matter. Surrounding the Milky Way is an enormous dark matter halo, extending far beyond the visible stars. Its gravity shapes the rotation of the galaxy, stabilizes the disk, and governs interactions with nearby galaxies. Without it, the Milky Way would be a fragile structure, vulnerable to disruption, unable to retain the billions of stars that orbit within it. Observations of galactic motion rely on precision measurements. Radio telescopes trace neutral hydrogen clouds, mapping the spiral arms and rotation curves. Space observatories like Gaia chart the positions and velocities of billions of stars, revealing streams, clusters, and substructures that record past interactions. Even in the vast emptiness of space, the history of movement is written clearly for those who know how to read it. The Milky Way's motion is a reminder that galaxies are not static backdrops to the universe. They are dynamic, evolving systems. Their shapes, populations, and even chemical compositions are molded by rotation, interactions, and mergers. The galaxy we see today, the luminous band stretching across our sky, is a snapshot in time, the result of billions of years of motion and transformation. And as we look toward the future, we can envision the collision with Andromeda, the ongoing consumption of smaller galaxies, and the ever-turning spiral arms, a cosmic story that is still unfolding. In this chapter, we have explored the Milky Way as a dynamic, moving system, shaped by rotation, interactions, and the gravitational influence of dark matter. We have traced the trails of past mergers, envisioned the cataclysmic future with Andromeda, and seen how the galaxy's motion underpins every aspect of its structure and evolution. The Milky Way is alive, not just with stars, planets, and gas, but with the ongoing motion that defines its very existence, a celestial dance billions of years in the making. Extreme phenomena, pulsars, black holes, and stellar explosions. The Milky Way is not merely a serene collection of stars and planets. Hidden within its spiral arms, disk, and halo are the remnants of extraordinary cosmic violence, extreme phenomena that illuminate the raw power of the universe. These events are both destructive and creative, shaping the galaxy in ways that are often invisible to the naked eye, but revealed through careful observation across the electromagnetic spectrum. Among the most fascinating of these objects are pulsars. Born from the collapsed cores of massive stars after supernova explosions, pulsars are rapidly rotating neutron stars with magnetic fields billions of times stronger than Earth's. As they spin, they emit beams of radiation, sweeping across space like cosmic lighthouses. Observed as regular pulses, sometimes hundreds of times per second, pulsars are natural clocks, their precision unmatched by human technology. The Vela pulsar, located in the southern sky, is a striking example. Its energetic emissions and rapid rotation provide insights into the physics of matter under conditions impossible to replicate on Earth. Black holes, too, are scattered throughout the Milky Way, both stellar mass remnants of collapsed stars and the supermassive giant anchoring the galactic center. Cygnus X1, one of the first black holes identified in our galaxy, lies about 6,000 light-years from Earth. Its presence is revealed by the gravitational effects on its companion star and the intense X-ray emissions as gas spirals into the event horizon. Black holes are extreme laboratories, regions where space and time are warped, where gravity dominates over all other forces, and where matter and energy behave in ways that challenge our understanding of physics. Supernova remnants also decorate the Milky Way, relics of stars that have ended their lives in catastrophic explosions. The Crab Nebula, the remnant of a supernova observed in 1054 AD, continues to expand, glowing brightly across optical, radio, and X-ray wavelengths. Within it, a pulsar spins at an astonishing rate, energizing the surrounding gas and producing intricate filaments. Supernovae are not mere deaths. They are cosmic recycling engines, distributing heavy elements into the interstellar medium, enriching future generations of stars and planets. Some of the most energetic events are gamma-ray bursts, brief but intense flashes of high-energy radiation that, for a few moments, outshine entire galaxies. Though rare within the Milky Way, their study informs us about the collapse of massive stars and the formation of black holes, providing a window into processes that release energy in quantities almost unimaginable. Even the Fermi bubbles, enormous lobes of gamma-ray emission extending above and below the galactic center, reveal the interplay between supermassive black holes, stellar winds, and cosmic rays on a galactic scale. These extreme phenomena, though violent, are essential to the evolution of the Milky Way. They sculpt the interstellar medium, trigger star formation, and contribute to the chemical enrichment necessary for planets and life. Without supernovae, heavy elements like carbon, oxygen, and iron would remain locked inside stars. Without black holes, the dynamics of the galaxy's core would be profoundly different. Every eruption, every pulse, every energetic outflow is a testament to the immense power that courses through our galaxy. Modern astronomy allows us to study these phenomena in remarkable detail. Observatories like Chandra, Fermi, and Hubble capture radiation across the spectrum, revealing hidden structures and energetic processes. Radio telescopes map the intricate patterns of pulsars and supernova remnants. Infrared observations penetrate dust to reveal star-forming regions influenced by these extreme events. Together, these tools provide a holistic view of the Milky Way, a galaxy alive with energy, motion, and transformation. In this chapter, we have explored the extreme side of the Milky Way, the pulsars spinning like cosmic clocks, the black holes warping space, the supernova remnants and gamma-ray bursts that light up the galaxy with energy unimaginable. These phenomena are reminders that the universe is not merely a backdrop for our existence, but an active, dynamic arena of creation and destruction. The Milky Way, for all its beauty and serenity, is also a realm of power and violence, where forces far beyond human comprehension continue to shape the fate of stars, planets, and entire regions of the galaxy. The future of the Milky Way, evolution, decline, and cosmic collisions. The Milky Way, magnificent as it appears today, is not eternal in its present form. Like all galaxies, it evolves, ages, and changes over cosmic time. Stars are born and die, gas clouds are consumed or expelled, and the galaxy itself is destined to interact with its neighbors. To understand the future of our home in the universe is to glimpse billions of years ahead into a future shaped by gravity, energy, and chance. Star formation, the engine that drives the growth and luminosity of the Milky Way, is gradually slowing. Molecular clouds, the raw material for new stars, are steadily depleted, either by the formation of stars or by expulsion from stellar winds and supernovae. Regions like the Orion Molecular Cloud Complex will eventually exhaust their supply of gas, leaving only the residual stars behind. Over the next few billion years, the rate of star formation in the Milky Way will decline, leading to a quieter, older galaxy dominated by long-lived stars such as red dwarfs. Meanwhile, the existing stellar population will continue to evolve. Massive stars will burn out and explode as supernovae, enriching the interstellar medium with heavy elements, while low-mass stars will quietly fade into white dwarfs, their heat gradually radiating away into the void. Neutron stars and black holes will remain, remnants of the galaxy's violent past, while the overall luminosity of the Milky Way slowly diminishes. The galaxy, once radiant with energetic birth and death, will gradually enter a more subdued phase, a cosmic twilight. But the most dramatic change awaits in the distant future, the anticipated collision with the Andromeda Galaxy. Currently, Andromeda lies roughly 2.5 million light-years away, moving toward us at hundreds of kilometers per second. In approximately 4 billion years, the two galaxies will begin a slow, majestic merger, stretching over millions of years. Stars, gas, and dark matter will interact, spiral arms will warp, and tidal forces will fling some stars into new orbits or even eject them into intergalactic space. While individual stars are unlikely to collide directly, the gravitational dance will reshape the galaxies entirely, forming a new, more massive elliptical galaxy, a cosmic fusion of two spiral giants. During this merger, the interstellar medium will ignite in bursts of star formation, as gas clouds collide and compress. Massive stars will form and die in rapid succession, generating supernovae and enriching the newly formed galactic environment. Central black holes from both galaxies may eventually merge, releasing tremendous energy in the form of gravitational waves, ripples in spacetime that propagate across the cosmos. The Milky Way, as we know it, will be fundamentally transformed, yet its essence, the stars, planets, and remnants of previous generations, will survive in a new cosmic architecture. Beyond this grand collision, the future of the Milky Way is one of gradual decline over tens to hundreds of billions of years. Star formation will cease as gas is exhausted, leaving a galaxy dominated by long-lived red dwarfs and the remnants of more massive stars. White dwarfs will cool to black dwarfs, and neutron stars and black holes will remain as eternal relics. Galaxies within the local group will continue to interact, merge, and disperse, with the Milky Way's descendants becoming part of an ever-changing cosmic landscape. Speculation about even further futures, the trillion-year timescale, paints a picture of a universe growing dark and cold. Stars will die, galaxies will drift apart due to cosmic expansion, and black holes may eventually evaporate via Hawking radiation. The Milky Way, in its evolved form, will become a silent witness to the passage of time, a fading memory of the vibrant, star-filled spiral we inhabit today. Yet even as the Milky Way ages, the legacy of its stars, planets, and cosmic phenomena endures. The elements forged in supernovae, the chemical foundations of planets, and the possibility of life on distant worlds, all are traces of its active, evolving history. Every photon emitted, every gravitational wave rippling through space, every star forming in a molecular cloud is part of a grand narrative that spans billions of years. The future may see the galaxy dim, merge, and transform, but its story of creation, destruction, and cosmic evolution will echo across the universe for eternity. In this chapter, we have contemplated the Milky Way's future, from the gradual decline of star formation to the cataclysmic merger with Andromeda, and beyond to a universe where galaxies age and fade. The Milky Way is a dynamic system, alive not just in the present, but across billions of years, its evolution a testament to the forces that govern all cosmic structures. It is a reminder that galaxies, like stars and planets, are temporary yet eternal in their influence, shaping the cosmos in ways that endure long after their light has faded. The Milky Way as a cradle for life, amidst the spiraling arms, the glowing nebulae, and the dense clusters of ancient stars, the Milky Way serves as more than a cosmic spectacle. It is a potential cradle for life. For billions of years, the galaxy has nurtured conditions capable of giving rise to complexity, chemistry, and perhaps consciousness itself. Understanding how life might emerge within this vast expanse is to confront both the science of the cosmos and the profound question of our place within it. Life as we know it requires three critical ingredients: chemical richness, energy, and stability. The Milky Way provides all three. Heavy elements like carbon, oxygen, nitrogen, and iron, essential for planets and biological molecules, have been synthesized in generations of stars and scattered across the galaxy by supernovae and stellar winds. This recycling of material ensures that regions forming new stars today are enriched with the building blocks of life, a cosmic inheritance from ancient generations. Energy, too, is abundant. Stars emit light and heat, driving chemical reactions on surrounding planets. Radiation, both visible and invisible, interacts with atmospheres, oceans, and surfaces, potentially fueling prebiotic chemistry. Even high-energy phenomena, once thought hostile, may play a role in shaping the chemistry of planetary environments, producing complex molecules in ways still being explored by scientists. Stability is perhaps the most critical factor. The Milky Way's structure offers regions of relative calm where planetary systems can endure for billions of years, allowing life the time it needs to develop complexity. The Sun's position, roughly midway from the galactic center, exemplifies this galactic habitable zone. Too close to the center, and intense radiation, frequent supernovae, and dense stellar populations could strip planets of atmospheres or irradiate surfaces. Too far, and the abundance of heavy elements necessary for planet formation declines. Our solar system sits in a sweet spot, a cosmic oasis within the Milky Way. Exoplanet discoveries have revealed worlds of staggering diversity, many residing in conditions potentially suitable for life. The TRAPPIST-1 system, with its Earth-sized planets in the habitable zone, demonstrates that life could emerge around stars smaller and cooler than our Sun. Proxima Centauri b, orbiting the nearest star to our own, tantalizes with possibilities. Even gas giants, while inhospitable themselves, may host moons with oceans, magnetic fields, and atmospheres, hidden niches where life might thrive. The Milky Way is a galaxy teeming with potential, a vast laboratory of biological opportunity. Life in the galaxy is not confined to planets alone. Comets and asteroids carry complex organic molecules across interstellar space, seeding young worlds with prebiotic chemistry. In the early history of the solar system, such deliveries may have played a role in the emergence of life on Earth. Similar processes may occur throughout the Milky Way, distributing the ingredients for life wherever conditions allow. Yet the Milky Way is also a galaxy of challenges. Radiation from supernovae, black holes, and cosmic rays can threaten life on exposed worlds. Gravitational interactions may destabilize planetary orbits, and nearby stars can strip away protective atmospheres. Life, if it emerges, must navigate this dynamic environment, adapting to the interplay of cosmic forces, energy, and chemistry. The human significance of this understanding is profound. Looking up at the Milky Way on a clear night, we are not merely observing a band of stars. We are witnessing the context in which life arises and evolves. Every atom in our bodies, carbon, nitrogen, oxygen, was forged in stars long before the Earth existed. We are, in a very real sense, children of the Milky Way, products of its dynamic processes, and witnesses to its ongoing story. Exploration of the Milky Way as a cradle for life bridges science and philosophy. It challenges us to consider the rarity and resilience of life, the vastness of potential habitats, and the fragility of our own existence within this immense, interconnected galaxy. Whether life exists elsewhere or not, our presence here is a testament to the intricate balance of forces and elements that have made this galaxy a home for consciousness and curiosity. In this chapter, we have explored the Milky Way as a potential host for life, examining the chemical, energetic and structural conditions that allow complexity to arise. We have seen how stars, planets, and cosmic processes intertwine to create niches where life could flourish, and how our own existence is intimately tied to the galaxy's history. The Milky Way is not merely a backdrop to life. It is an active participant in its emergence, a cradle in which the story of life has unfolded and continues to unfold amidst the vast expanse of stars. Observing the Milky Way, humanity's window to the galaxy for millennia, the Milky Way has captivated human imagination. Long before telescopes, it was a mysterious band of light stretching across the night sky, a river of stars, shimmering and elusive, inspiring myth, art, and wonder. Ancient civilizations looked upward and saw stories reflected in its light, pathways of gods, rivers of creation, or bridges between worlds. From the Babylonians to the Greeks, the Chinese to the Mayans, the Milky Way has been a canvas upon which humanity projected its earliest understanding of the cosmos. The scientific study of the Milky Way began with careful observation and measurement. Galileo, in 1610, peered through his telescope and resolved the Milky Way into countless stars, revealing that this band of light was not a cloud, but a galaxy made up of innumerable suns. His revelation transformed human perception, showing that the universe was far larger and more complex than imagined. It was the first step in humanity's long journey to map and understand our galactic home. Modern astronomy has extended this vision across the electromagnetic spectrum. Optical telescopes reveal the stars that make up the spiral arms. Radio telescopes trace clouds of neutral hydrogen, unveiling the structure and rotation of the galaxy. Infrared observations penetrate dust-obscured regions, uncovering hidden star-forming regions and the bustling galactic center. X-ray and gamma-ray telescopes detect the energetic phenomena of black holes, supernova remnants, and pulsars. Each wavelength is a lens, allowing humanity to see the Milky Way in ways invisible to the naked eye. Satellites and space missions have transformed our understanding further. The Hubble Space Telescope has captured unparalleled images of star clusters, nebulae, and stellar nurseries. The Gaia mission, launched in 2013, is mapping the positions, distances, and motions of over 1 billion stars with unprecedented precision, providing a three-dimensional view of the galaxy's structure. These observations allow astronomers to reconstruct the Milky Way's history, trace stellar migrations, and predict its future, bridging the gap between myth, imagination, and empirical science. Beyond the science, the Milky Way remains a deeply human experience. On clear nights away from city lights, the galaxy arches overhead in brilliant splendor. Each point of light represents a distant sun, perhaps with planets, perhaps with life. Our ancestors stood beneath the same stars, pondering their place in the cosmos, drawing stories in the night sky. Today, with telescopes and satellites, we stand in the same wonder, now armed with knowledge, yet still humbled by the scale and majesty of the galaxy. Different cultures have interpreted the Milky Way in unique ways. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, while the Norse imagined it as the path to Valhalla. Native American tribes saw it as a trail of spirits, guiding souls across the heavens. The Chinese depicted it as the Silver River, connecting stars in intricate patterns. Across time and space, the Milky Way has been both a source of inspiration and a guide, a reflection of humanity's desire to understand the universe and our place within it. Science and culture converge in the act of observation. While technology allows us to measure, map, and model the galaxy, the human experience of gazing at its luminous band remains profound. It reminds us that we are part of something far larger, that our story is intertwined with the stars, and that curiosity and wonder are as fundamental to our species as the elements that form the planets we call home. In this chapter, we have explored how humanity observes and experiences the Milky Way. From ancient myths to modern telescopes, from naked eye wonder to precise astronomical measurements, the galaxy continues to inspire, guide, and challenge us. It is both a scientific frontier and a cultural touchstone, bridging the vastness of the cosmos with the intimate experience of life on Earth. To look at the Milky Way is to witness the story of stars, the evolution of galaxies, and the enduring curiosity of humankind, a connection that transcends time, culture, and imagination. Mapping the Milky Way, unveiling the hidden architecture. For centuries, the Milky Way was a mysterious band of light, a ribbon of stars stretching across the night sky. To the unaided eye, it appeared as a simple luminous path, but in reality, it conceals a vast and complex structure spanning hundreds of thousands of light years. Today, astronomers are peeling back this veil, mapping the galaxy in 3 dimensions, uncovering its spiral arms, central bulge, halo, and the hidden dance of billions of stars. The first attempts at understanding the galaxy's structure relied on the positions and movements of stars. Early astronomers noticed patterns in the distribution of bright stars and star clusters, hinting at the existence of spiral arms. With the advent of radio astronomy, a new window opened. The neutral hydrogen gas in the Milky Way emits radio waves at a wavelength of 21 centimeters, invisible to optical telescopes, but detectable by radio arrays. By mapping this emission, astronomers could trace the location of gas clouds and delineate the spiral arms with unprecedented clarity. Today, missions like Gaia are revolutionizing our understanding of the Milky Way. By precisely measuring the positions, distances, and velocities of over 1 billion stars, Gaia provides a 3-dimensional map of the galaxy, revealing its contours, motions, and hidden substructures. Stars are not randomly distributed. They cluster in spiral arms, follow orbital patterns around the galactic center, and form streams that trace the remnants of galaxies consumed long ago. Every star carries information about the history of the Milky Way, its composition, and its place within the cosmic tapestry. The spiral arms themselves are regions of active star formation, dense concentrations of gas and dust, triggered by spiral density waves, collapse under gravity to birth new stars. Young, luminous stars illuminate the surrounding clouds, making the arms visible in optical and infrared observations. The Orion Arm, where our sun resides, is a minor spiral arm, yet it hosts numerous star-forming regions, clusters, and molecular clouds. This arm is our galactic neighborhood, a bustling area where stars and planets are continually being created. The central bulge of the Milky Way presents a different story. Dominated by older, redder stars, This densely packed region surrounds the supermassive black hole, Sagittarius A. The bulge is a relic of the early Milky Way, a record of ancient star formation and the gravitational forces that shaped the galaxy. By studying the composition and motions of these stars, astronomers can infer the processes that occurred during the galaxy's formative years, piecing together the Milky Way's origin story. Beyond the disk lies the galactic halo, a sparsely populated spheroidal region containing ancient stars, globular clusters, and the elusive dark matter that governs the galaxy's rotation. Stellar streams, remnants of dwarf galaxies torn apart by tidal forces, wind through the halo, leaving traces of past mergers. These structures serve as a cosmic archaeological record, allowing scientists to reconstruct the Milky Way's violent and complex history over billions of years. Galactic archaeology, as this field is known, relies on measuring the ages, chemical compositions, and motions of stars. Older stars, poor in heavy elements, tell of an era when the galaxy was young and less enriched. Younger stars, abundant in metals, reflect the recycling of material from previous generations. By mapping these populations across the galaxy, astronomers can identify the locations of ancient mergers, star formation bursts, and even the influence of dark matter on stellar orbits. Observations across multiple wavelengths reveal layers invisible to the naked eye. Infrared imaging penetrates dust-obscured regions, revealing the dense clusters near the galactic center. X-ray and gamma-ray observations expose energetic processes, such as supernova remnants and black holes, shaping the interstellar medium. Radio observations trace molecular clouds, the raw material for future stars. Together, these methods provide a comprehensive view of the Milky Way, uniting structure, dynamics, and evolution in a single, cohesive picture. Mapping the Milky Way is more than an exercise in cartography. It is a journey into understanding the galaxy's past, present, and future. Each star, each cluster, each gas cloud serves as a data point in a grand story spanning billions of years. By unveiling the hidden architecture of the galaxy, we not only learn where stars and planets reside, but we also uncover the forces, events, and processes that have shaped the Milky Way into the magnificent spiral we inhabit today. In this chapter, we have explored the techniques and discoveries that reveal the Milky Way's structure. From early optical observations to the precision mapping of Gaia, from spiral arms alive with star formation to ancient globular clusters in the halo, the galaxy emerges as a dynamic, interconnected system. Every measurement, every map, every new discovery brings the Milky Way into sharper focus, allowing humanity to understand not only our place within the galaxy, but also the story of the galaxy itself, a story of creation, evolution, and cosmic wonder. Dark matter, the invisible sculptor of the Milky Way. Beneath the shimmering stars and glowing nebulae lies a hidden, invisible force that dominates the Milky Way. Dark matter, unseen yet omnipresent, shapes the galaxy in ways that are fundamental and profound. Though it neither emits nor absorbs light, its gravitational influence is unmistakable, governing the motions of stars, the stability of spiral arms, and the very architecture of our galaxy. The first hints of dark matter emerged in the 1970s, when astronomer Vera Rubin and her colleagues measured the rotation curves of spiral galaxies, including the Milky Way. They discovered that stars far from the galactic center moved far faster than expected if only visible matter were present. Gravity, it seemed, was being supplied by something unseen, a mysterious substance spread throughout the halo, invisible to telescopes but dominating the galaxy's mass. In fact, estimates suggest that more than 80% of the Milky Way's mass exists in this invisible form. Dark matter is not confined to the disk of stars. It forms an enormous halo, enveloping the galaxy and extending well beyond the visible spiral arms. Within this halo, dark matter exerts gravitational forces that maintain the rotation of the galaxy and influence the trajectories of stars, gas clouds, and even satellite galaxies. Without dark matter, the Milky Way's structure would unravel, stars at the edges would drift away, and the spiral arms would lose their elegant coherence. Yet dark matter remains elusive. It does not interact with light, heat, or ordinary matter in ways we can easily detect. Its presence is inferred from gravity alone, from the motions of stars, the bending of light in gravitational lensing, and the dynamics of galaxy clusters. Experiments deep underground and in space continue to search for direct evidence, probing the fundamental nature of this cosmic mystery. Understanding dark matter is one of the greatest quests of modern astrophysics, for it holds the key not only to the Milky Way's structure, but to the composition of the universe itself. Dark matter also influences galactic evolution. Its gravitational scaffolding guides the formation of spiral arms and bars, channels the infall of gas, and affects the merger history of the galaxy. When dwarf galaxies approach the Milky Way, their paths are dictated by dark matter, determining how they are torn apart and assimilated. Stellar streams, remnants of these past collisions, are shaped by the unseen halo, revealing the hidden contours of this invisible mass. On larger scales, dark matter connects the Milky Way to the cosmic web, the vast network of filaments and voids that structures the universe. Galaxies are not isolated. They form and evolve within this dark framework, their positions, interactions, and mergers influenced by the unseen hand of dark matter. By studying our galaxy, we gain insight into these universal processes, understanding how luminous matter dances within the shadow of the invisible. Observational astronomy continues to refine our understanding of dark matter in the Milky Way. Surveys of stellar motions, such as those conducted by Gaia, allow astronomers to map the gravitational field across the galaxy. Computer simulations model how dark matter interacts with ordinary matter over billions of years, revealing how spiral arms, bars, and halos emerge from these interactions. Each measurement brings us closer to visualizing the invisible, unveiling the true skeleton upon which the galaxy is built. The philosophical implications are as profound as the scientific ones. Most of the mass of the Milky Way, and indeed most of the mass in the universe, remains invisible to us. Humanity's experience of the galaxy, luminous stars, planets, and nebulae, represents only a fraction of its substance. The majority lies in the unseen, reminding us of the limits of perception and the vast mysteries that remain beyond our senses. To understand the Milky Way is to acknowledge the beauty and power of the invisible, the hidden forces that shape existence itself. And that's where we'll pause for today. I hope you enjoyed this little long journey into the Milky Way. We'll continue the next part tomorrow, so make sure to come back, get comfortable, and drift into more sleepy science facts with us. Until then, rest well, stay curious, and I'll see you in the next episode.